Okay, so we're recording. Let me open a PowerPoint and let's talk a little bit about what we're doing this week. Um, so this week we're talking about rotation, and the issue with rotation is that we have to have a brand new set of variables and a brand new kind of understanding of our coordinate system. And that ends up being a little bit hard to grasp. The good thing is we already know how to do uniform circular motion. We did that like twice. And so our job here is that we need to come up with equations to describe rotation. And so how we do that is just, if we have something rotating, let's say we have a point mass. The most important thing to understand, first of all, is you have to choose an axis. And when we draw like Y or X, the normal ones that you have done forever, the Z axis positive comes out of the page towards you. So this Z vector I drew is coming toward you, and the negative Z goes into the page. And just like on a normal XY graph, if this is your X-axis and this is your Y, we take positive rotations around. So if something like a particle is rotating around this Z-axis, so going around in a circle, we draw the Z vector is our omega, and omega is the angular acceleration. We'll talk about that in a minute. But you always have to have an axis. When you talk about rotation, you always have to talk about rotation about an axis. Positive coming out of the page means it's going clockwise. Negative means it's going the other way. And how you can remember that is if you just remember the XY plane that you've always done, you know that going this way would be a negative angle, right? The change of angle would be negative. The other way, if you can see my hand, is if you point your thumb at yourself, when you curl your fingers with your fist, as you curl it, hi Araya, your microphone's on. When you curl your fingers into a fist, that's positive. And so if you put your hand so that your thumb points into the screen, your fingers turn the negative direction. So into the screen negative, out of the screen positive. And that doesn't mean anything because essentially if I had something spinning on the table, spinning around on the table like this, I could say that this thing is rotating and my thumb up is the positive rotation. Just know that you need to have, you have to choose an axis. If we go back to uniform circular motion and we have something that going around in a circle, okay? So it moves from point 1 to point 2, right? We're always going to consider that the R vector, the radius from the origin where our rotation is constant. So we'll always have constant R. There's a change of angle from P1 to P2, and this length along the circumference we call S. It's called the arc length. And I talk about this in the video. If you take in calculus, you probably already had to do like an integral for a really weird curve and you had to do the arc length of that curve. The beautiful thing that we have is we're going to consider R to, R to be always constant. And if R is constant, then it makes the arc length super easy because you already know that if this is true and R is constant, the arc length is simply R times the change of theta. And we really should call this delta S. So this is how far around the circle it travels. R is constant, and you have a change of angle. Now in rotation, we have our dependent variable x is replaced by theta. And then we use those same equations you knew from projectile motion or constant acceleration to find things like the velocity and the acceleration, except they have different names. So ds dt, if I take the time derivative of this side, we know along the curve at every point it has a velocity that's tangential to the curve. That's what ds dt gives you, is it gives you the velocity, but we call that tangential velocity. And back when we learned uniform circular motion, we found that there was this arad, and that arad was b translational over r, and that a of t is just dbt over dt. Okay, so hopefully you understand all those things. What this tells us, though, is that if we have s is equal to r theta, then ds dt is equal to r d theta dt. And the change of theta is something that we call omega. And I always put just a little circle to remind me that omega has to be rads per second for this to be meters per second. It cannot be, and I talk about this in the lecture, but it cannot be in degrees, okay? Because what essentially omega is the change of angle over the change of time. This can't be in degrees, it has to be in radians. Radians are actual numbers, degrees are not. So this has to be in radians over t, so this has to be in radians. If we take the time derivative of this again, and you'll see why we're doing this in a second, what we get here is the tangential acceleration, the acceleration along the curve, if v is changing. V doesn't have to be uniform anymore. And this is something called alpha. And alpha is d omega dt, or it's the second derivative of the position with time squared. All that, really the only thing you need to take out of this, and you'll see this later when we do problems, is that s is equal to r times the change of theta, the distance around a rotation. V can be related to omega through this equation, and a can be related to alpha. So what we're going to do is we'll have something like a pulley that rotates, and this block will be moving down with a, and the pulley will be rotating with alpha. And you can set alpha is alpha is, I'm going to write it r alpha. R alpha is a at the edge. So a would actually, little a would change the closer you got to the radius, the smaller this r is. What that means is, we talked about this when we did uniform circular motion, but you know that a point here, if they're rotating with the same alpha, this point has to travel slower because it doesn't have as far to go around. Alpha is the rads per second squared. One rotation is 2 pi, right? One revolution or rotation is 2 pi rad. So if alpha is the same for both of these, it takes them the same amount of time to go around. This guy would have to have a faster a because it has to travel a greater distance. But what that tells you is that r alpha at the edge is equal to a, and you can then equate this a and this a. And you'll see that when we do the actual problems. But this is really the only thing you need to remember. And then, because if we just change x for theta, we get these standard equations that you already know. And finally, we never use this one, but So these are just the same equations that you had for the y when we did projectile motion or the constant accel, because we're always going to assume that forces are causing torques and that they're constant. So if it's constant angular acceleration, you can figure out the change in angle, and it's usually easier to just call this delta theta. But you can find the initial or final omega, angular velocity. If it starts from rest, this would be 0, this would be 0. So you can find time. Just make sure you know how to do that for like a CD spinning up or whatever. Okay, so all that's well and good. What I really need to talk about, though, is how this works with torque. So let's talk about what torque actually is. The example I always use, and I hope you've all used a wrench. Okay, so a wrench, you're trying to turn some bolt. And let's say the z-axis comes out, so you're trying to turn this bolt counterclockwise, which we say is positive. So we want this thing to turn with positive omega and positive alpha. Okay. How do we do that? Well, if you pulled on this wrench or you pushed on it, right, this thing wouldn't turn. So when we call this the lever arm is R, and it's the distance from where we apply the force. That R, if that R and F were parallel to each other, nothing would happen. It wouldn't turn, right? You could, I guess, push it or pull it, but what has to happen is you have to have a force that is at least has some component perpendicular to your lever arm. So how you draw this is you draw the vectors tail to tail. You put them tail to tail, right? And then you do the cross product. And the cross product has to be R cross F. It has to be in that order. What this is saying is that you turn R to F by the shortest angle. You wouldn't go this way, you go this way. And we see that this rotation, if you use your right hand, take your fingers and turn R to F. So your fingers are like R and they have to rotate to F. Your thumb is pointing toward you, which means that we're rotating around this axis with positive omega or positive alpha if we're rotating around, okay? RF is equal to RF sine of the angle between R and F. But what that's really saying is, in a second example, let's say the force is at 30 degrees and my R is along the x-axis. So instead of this force, we have a force that's like at 30 degrees. We need to take the perpendicular component. That's what this is. And then F, if we break into Fx and F sine, right, Fy, Fx is F cos, and F sine is Fy is F sine. On a cross product, if the angle's 0, you get nothing, right? So this has to be R times F of Y, which is R F sine of the angle, okay? It's positive because the angle between R and F sine, or Fy, is positive, right? The other way that you almost never do here is the cross product, if you're in 2 dimensions, gives you Rx Fy minus Ry Fx, and Fy is F sine theta. There is no Ry, so this would cancel for us, and it's in the z hat direction, and that tells you it's positive. If these were flipped, if for instance the wrench were upright, and I was trying to turn it with a force in this direction, so this is my R, and this is again my z hat, right? But now I see that I'm turning backwards. So I'm actually going negative omega and negative alpha. If I do R cross F, I put R and F tail to tail, and I rotate R to F. I can see that this is a negative delta theta. So my torque, which is R cross F, gives me RF sine of the angle between R and F. But I know that this angle between R and F is minus 90, and I would get negative RF, whatever R and F happen to be. So the things to remember is it's always R cross F. You can find the angle by using the right-hand rule. Is usually the easiest. If R turns to F clockwise, it's negative. If R turns to F counterclockwise, is positive. There's one of the homework that I did today that has like it gives you an R that can change. So you have some R, and then this is like a disk, and they're saying that right here, you're gonna apply a force at 25 degrees, let's say. And one of the questions that it asks you is, since you can rotate this force anywhere along this edge, is it says, when is the torque minimum? And if you understand this, you understand torques. This would be a minimum when R and F are parallel to each other, right? When the angle between R and F is 0. So this has to happen when, if this is 25 degrees, when R is also at 25 degrees, so that they lie along a parallel line. This would not cause our object to rotate, because all you're doing is pulling on it, right? You're pulling in the translational direction, or the direction parallel to the edge. Here, it would, because when you break this force up, this force would have an Fy that's F sine of 25, and an Fx that's F cos of 25. And the angle between F and R only has an Rx. So you would get R cross F is R times Fy, R F sine of 25, which in this case, if I put them tail to tail, 25 is the angle between them, right? The angle of RF would be 25 degrees. And it would be a maximum when R and F are perpendicular. So that would happen when F is at 25 and R, between R and F, this angle is 90 degrees, okay? So make sure you understand that question. It's one of those interactive ones that you have a couple little sub-questions to answer. But basically what you need to remember for torque is that torque is R cross F, which is really RF sine of the angle between them in the z-hat direction. And you need to figure out by the right-hand rule, is it positive or negative? Most of the time, we're gonna have things like pulleys where there'll be a tension, right? The torque here, if this pulley has a radius, then I have an R vector, and the force acting on that pulley due to that tension is that tension down. If I move these, I see that I have R and I have a tension. If I want to figure out what this torque is acting on this pulley, R cross T, the angle between them is 90 degrees. So this is RT sine of 90 degrees. This is 1, right? And it's positive 1. So this torque, due to this tension on the pulley, is RT. Most of the time, that's what's going to happen. We're going to have an R vector of the object and a force acting on it at an edge, and you'll be able to do that. The next thing to understand is that torque is actually equal to something called I alpha. And now here's where the physics actually is. We used to do a lab, or we do a lab, where you have to give the Newton's second law equivalence for torque. And we know that F equals ma. We learned that already. Well, torque works the same way, but it doesn't. And here's the thing. A torque is I alpha. And I ends up being equivalent, well, let's write this. So the acceleration due to a force is the force divided by the mass. And so from this, I don't know if you guys remember, like the first lecture I asked what mass was. Well, mass is how much a object or system resists being accelerated by a force. It's a measure of what we call the inertia. Same here. So if we want to know the rotational acceleration, that is torque over moment of inertia. What moment of inertia is it's how much a object resists being rotated. But I isn't as simple as M. It's not just mass. And the reason for that is the further away a object is from some axis of rotation, which we'll just call Z hat. So if this is R and this is R2, right? And this is M1 and this is M2, the further away it is, the harder it is to get it to rotate. And it turns out that I is equal to mr squared, usually with some number in front of it if it's an object. Now here's the deal with I. So we need to be able to figure out, one of the things you need to be able to find is you need to be able to figure out for an object, what is I? And we'll talk about that in a little bit. But I usually has some number in front of it for an object. For a point mass, it's mr squared. Remember in chapter 7 or 8, we had to find center of mass? I is very similar to center of mass, because if you remember that the center of mass was mr center of mass, and this was the total, and this was mr plus mr plus mr. This is kind of the same thing, except that I for a point mass is mr squared. And how you find R is you choose an axis, some Z hat, and you figure out where M is rotating, at what distance it's rotating from that axis. You can figure out with a integral, R squared dm, you can find the moment of inertia along R for any object doing an integral. I show you how to do that, but in this class, we don't have to do that. The reason why is, number one, those integrals can be really ugly if you try to figure out some solid. If you guys haven't done solids of revolution in calculus, they're horrible. Trying to do just a cone is a pain. Imagine doing some weird shaped base, right? Or some weird shaped blob. What we're going to use is we're going to use symmetric objects. So we're going to use things like a disk or a sphere, or a hollow sphere that has like a thin shell, or we'll use a cylinder, or we'll use a rod, all these things. We have in chapter 10, there's a chart that gives you these moments of inertia. However, I want to tell you something. If you don't know what the moment of inertia is, if you're taking, say, the MCAT, and you can't remember the moment of inertia and you need it, you can almost always just go mr squared over 2. I'm going to talk about this for a second. Imagine that you have a coin and you lay it flat on a table and you make it spin around. It spins around an axis through its body, right? Or imagine a wheel that's rolling along the road and it's rotating around a center body axis. The I for that is mr squared over 2. If it were a cylinder, it's still mr squared over 2. And the reason why that is really what the moment of inertia tells you is how the mass is distributed relative to the axis. So if you remember a point, just a point mass is mr squared. A disc or a wheel is mr squared over 2. So this is our pulleys. And we're going to do a bunch of problems with pulleys where this will be our I. Same for a cylinder. It doesn't matter how long the cylinder is. The only thing that matters is that the body axis passes through the face, which is exactly distributed like a disc. However, I could take a coin and put it on its edge, right? And spin it around its edge. So basically I spin it upright. I don't have a coin with me, but if I could spin it upright, this is actually mr squared over 4. And the reason why is that the mass is actually distributed closer to the axis. Here, it's distributed uniformly in a circle, right? At every point, the mass distribution is the same. Here, this mass and this mass maybe at the edge are very different, and more of the mass actually lies next to the axis. So I get a smaller I. mr squared over 4 is smaller than mr squared over 2, right? The more mass you have near the axis, the easier it is to rotate that object. And then the one big one is if you have a rod, and this is where things are going to get kind of weird and complicated. We always take the center of mass, so what we call the ICOM, which is actually what these are, if it's rotating through the center of mass on that axis. For a rod, we assume it's uniform, and we assume that it's rotating through its center of gravity, the point where the mass could treat the object as a point mass. Here for a rod, this is ml squared over 12. Now, say I want to move the axis, though, to the edge. So I want to know what it is when I move it to here. And I show you in the lecture notes. I believe it's in your book. If it's not in your book, you can find it. But when you move from here to here and make this thing, so this one's rotating like a baton twirler, spinning it in the center. This is now the whole thing is rotating around. When it moves, I is equal to ml squared over 3 around an n, okay? There's a few more, like a solid sphere is, I believe, 2 2/5, no, 2/3, whatever it is, you can look it up. If the sphere were hollow, it would be 2/5 mr squared, something like that, whatever it is in your book. You just look up what I is when it's going through that axis. And so for a rod, it has different moments of inertia depending on what axis you're taking through the rod. Now, for the rod, when I talk about an axis, if I go through the center and this thing rotates around, I could choose another parallel axis at any point, and I can figure out what the moment of inertia is around any other parallel axis, so it's in the same direction as z, but located somewhere else on the rod, using something called the parallel axis theorem. And that's ICOM plus md squared. How you find this, I now, is you do, for the rod going through the center, which is ICOM, ml squared over 12 plus m times d squared. If I moved it a quarter of a way to the right, then d would be L over 4 squared. I would get ml squared over 12 plus m L over 4 squared. This would be L over 16, so I'd have ml squared 1 over 12 plus 1 over 16, whatever that happens to be. I'm not going to do that math. I should have chosen better. But 12 over 16, let me do it. 16 times 12 is 192. So this would be ml squared 16 over 192 plus 12 over 192, which is 28 over 192. Yeah, whatever that is, 0.14. So this would end up being ml squared times 28 over 192. That would be your I if we moved it a quarter of the way. And what it would look like is it would look like this thing was now rotating, instead of about the center, it's rotating at an axis that's at L to the 4th off the center. If we chose this to be our 0, it's now rotating there, okay? I show you how to do that. That's the parallel axis theorem. In the homework I gave you today, it talks about a meter stick. And it doesn't really explain this, but a meter stick has a length of 1 meter, obviously. If it were going through the center axis, I would be ml squared over 2, but L would be 1 meter. And so if I gave you a mass of, say, 2 kilograms, this would be 2 over 2 times 1 squared, which would be 1 kilogram meter squared. That's your units of moment of inertia, okay? And then it asks you, well, if I move it to some where d is, I don't know, 0.5 to the right, what I would have to do is find the parallel axis, which is ICM plus md squared. This would be 1 from here, because this is actually the center of mass. I'm sorry, that's over 12. So this is 1/6. 1/6 plus 2 times 0.5 squared, which is a half times a half. So this is a half. You get 1/6 plus 1/2, which is 4/6, which is 2/3. If I can write. Okay, so 2/3. The answer would be 2/3 kilograms meters squared. But the point here is that the parallel axis theorem, if you know the center of mass, moment of inertia, you can move that axis anywhere parallel to the original axis. So I could put it here, I could put it here, I could put it wherever. If I do that, then all I have to do is multiply the mass times the change of distance between the center of mass axis and the new axis that I want. There's a problem in that homework that I gave you today that says a meter stick and then they move it, and it doesn't really explain. If you're not paying attention, you'll be like, well, I don't know what to do. They gave you the length. So first figure out what this is for the mass given. And then when you move it, you need to find the new. But there's something else that makes it really, really simple to do moment of inertia. Imagine now that I have a rod, okay? And it's rotating about one end, and I know that that is ml squared over 3, about one end. Now though, I attach to it a sphere. And this sphere, I'm going to assume that the rod like goes into the sphere somehow. And so basically the center of the moment of inertia here is at L. The center of the sphere is at L, right? By the parallel axis theorem, ICOM plus MD squared. For a sphere, I said it was whatever. If it's solid, it's 2/3 mr squared plus ml squared, because I moved this thing. This would be 2/3 mr squared if it was at the axis of rotation, but I moved it. So this is now I parallel of the sphere. But the total of the whole system, all I have to do is get I of the sphere plus I of the rod. So my total is 2/3 mr squared, where this is the mass of the sphere, obviously. Mass of the rod, L squared. Mass of the sphere, L squared, plus mass of the rod, L squared over 3. The nice thing is that, no, you don't have to memorize them. You can look them up. They're in every physics book at this level, introductory physics with calculus. Every physics book has that table. They're everywhere online. If I haven't showed you guys this, I'm going to show you right now something that I think I showed you, but I want to show it to you again. And this is a really good opportunity. So if you go to hyperphysics, if for some reason maybe you're trying to do something and your textbook isn't there, hyperphysics, this is hyperphysics. It's run by Georgia State University or something. It's free. But you can go in and click on any of these topics. So I'm going to click mechanics. And I'm going to go to torques. And I'm going to go, this isn't what I exactly want. What I want is I want moment of inertia. So I can go to the index and look up moment of inertia here. Hopefully. Moment of inertia. So these are your moment of inertia about different axes. The red is the axis that it's rotating around, and this tells you for these shapes what they are. So for a hoop, if you're rotating around, like it's just rolling down the road, if it were to spin about some body axis here, it would be 1/2. If it was rolling, it's just mr squared, just like a point mass actually. For a wheel or a cylinder or whatever, it's 1/2 mr squared. If a solid cylinder rotated, you can see that it would be this. They give you some examples here. Sometimes they'll even have little widgets that you can plug in your answers. It also tells you the general form and how to find the general form for different types of objects, how to find it by integration. This website is a really good resource for our level of physics for how to do things if you want some extra tutorials, or if you forget something, if you forget how to do something and you realize you need it, right? It even covers like, so it shows, oh, if our position X becomes theta, our velocity becomes omega, A becomes alpha, the motion equations are these things, and it gives you all this nice stuff. Hyperphysics is a really good website run out of, as I said, I think Georgia Tech or somewhere like that runs this. And it's been online forever, and it covers everything. And you might actually find in 4B and 4C that you end up really, really liking this for explaining concepts to you, like electric potential energy, let's say. It tells you like zero potential references, things like that. It's a really, really nice website. So just keep in mind that it's there if you ever need it. To answer your question in chat though, Calvin, if I go back to moment of inertia, there's essentially this same chart. This same chart is in your book, and all you have to do is consult it when you need I. As I was saying though, where things get a little more complicated is that you can draw, or you could have a system with multiple shapes where you have to figure out the moment of inertia. And there's something called the principle of supposition. And what that means is that I total is equal to I1 plus I2 plus I3, as long as you find them around the same axis. So going back here, I for the rod plus the sphere about this axis is I of the rod about that axis plus I of the sphere about that axis. The problem is you need to use the parallel axis theorem to find it. So go to that chart and look up a solid sphere about its body, and that gives you ICM, COM, I of center of mass. Use the parallel axis theorem to shift that moment of inertia to about the axis, and then add them both together, the rod and the sphere. So here we had I of the sphere plus I of the rod. So that's all good. Once you do that, you find I, and we'll talk about how this all works in a minute. But are there any questions on finding I? Essentially, what you have to do is you have to find the center of mass, right? Find sphere about the center of mass, and then if you moved it to some parallel axis, you have to use the parallel axis theorem to find I. In practice, we probably will do that once. I'm going to show you a couple of quick examples, and hopefully you'll understand how it works from these examples. All right. Now, let's talk about one last thing, and that is, what does torque actually become? So if torque becomes I alpha, or torque is RF, look at the units here. These are newtons times meters. That's energy, but that's not energy. And the reason why it's not energy is you actually have to torque times a change of angle. So Newton meters times rads in rotation is energy. Newton meters is just the magnitude of the force, and it's not energy. It's not energy until you actually do something with it. This is like force normally, and force times distance gives us work, which gives us a change in kinetic energy. Well, torque times the change of angle, which is identical to I alpha in some ways, weirdly, gives us, so I alpha gives us a change in kinetic energy as long as we multiply it by something. We'll get into that. You'll see it's weird. I know it's weird. It's because you have this extra R term. If we look at this, mr squared times rads over second squared. This is kilograms meters squared over second squared times rads. That is kilogram meter second squared times meters times rad. This is that. So just know that I alpha gives you change in kinetic energy. RF just gives you the magnitude of the force. RF times a change in angle gives you I alpha. It's weird, I know. It's odd because rads aren't actually units, but this is true. Now, what is the kinetic energy of rotation? Kinetic energy of rotation is I omega squared over 2. For a point particle, this is for rotation. For a point particle, remember that mv squared over 2 is kinetic energy. But we know v is r omega, assuming that r is constant, rolling without slipping. So I get m r squared omega squared over 2. And what this becomes for a point mass is I omega squared over 2. So what that means is for an object that's rotating, let's say I have a block, right, that's sliding along a surface. And we would say the energy of this block, it has no MGH, it has no spring, so this would just be mv squared over 2, right? But if that were a wheel that could also rotate through its center, so it's rotating and translating. So it's moving with v as if the center of mass is moving with v to the right, but it's also rotating with omega. The energy now becomes mv squared over 2 plus I omega squared over 2. For an object that has, I don't want to do that. An object that has, let's say a wheel that has a mass of 3 kilograms, right? I, if we look at that table, is mr squared over 2, and it has a radius of 1 meter, let's say. So I would be 3 times 1 squared over 2, or 3/2 kilogram meter squared. Now, if these things had the same energy, so this has 10 joules of kinetic energy, this one has 10 joules of kinetic energy, okay? That means E is 10 for both of them. If this is 10, and let's say their masses are the same, this guy would have 10 joules is 3 times v squared over 2, or 20/3 is v squared, or v is equal to square root of 20 over 3. Now this one, I would have mv squared over 2. I need to convert this into v's. So I know that I to the half omega is v over r. R omega is v. So omega is v over r. So this is v squared over r squared. And so what I get here is I get m to the half plus I over 2r squared is v times v squared is 10 joules. This number is 3/2 plus I was 3/2, so 3/2 times 1/2 times 1 over 1 squared. So that's 3/4. 3/2 plus 3/4 is 9/4, right? So this is 10 is equal to 9/4 v squared, or v is equal to square root of 40 over 9. That is a different number. If I put that into my calculator, root 20 over 3 is 2.6. The square root of 40 over 9 is 2.1. So my block has a velocity of 2.6 meters per second if the kinetic energy is 10 joules. My wheel that's rolling would have mv squared over 2, which I said was, so v is 2.1 meters per second. This is 3 over 2 times 2.1 squared. 3 divided by 2 times 2.1 times 2.1. It would have 6.615 joules of kinetic energy of translation, meaning to the right, just the straight line motion of the center of mass, plus it would have I omega squared over 2, which is I to the half times v squared over r squared. Omega squared is that. If I look back, my I was 3/2, my r was 1, so this is 3/2 times 1/2 times 1 over 1 squared times 2.1 squared, and that's 3/4 times 2.1 times 2.1, and that's 3.3 joules, as it should be, 3.3075 meters per second. Sorry, joules. It says my internet connection is unstable, so if I lose you guys, I'm sorry. So what you can see here, and why I just did this, is the block is sliding from left to right, and it has kinetic energy because it's translating. It's just moving to the right of mv squared over 2, and that's equal to 10 joules. Because of the mass is 3, you can find that the velocity is 2.6. However, when it's a rolling object, like a rolling wheel, it has to split the energy between kinetic energy of rotation and kinetic energy of translation. Translation is the normal mv squared over 2. Rotation is I omega squared over 2. But you can always turn omegas into v's so that you don't have two different variables that you can't solve for. Practically for us, what this means is we just spent last week talking about how we just write down the different types of energies, right? At each point, at point A and at point B. And if there was work, well, and then we could say E initial is E final. And if it had some friction, remember that we would just add friction, right, to the final or subtract it from the initial. But now, if there's a rotating object, we just add another term for the rotational energy. That's all we have to do, adding a term for the rotational energy. Energy problems are exactly the same with things rotating. You just have to remember, if something's rotating, that you need this term to be added. You might have to turn this into V's, or you might have to turn the V's into omegas, and we'll see that in a minute. I'll show you that. But so this is just really an extension of what we did in 7 and 8, except now we have another term, okay? So let's look at how that works in 2 ways. Imagine you have a pulley with a mass hanging down. And so I'm going to call this, P is going to be the mass of my pulley. If you want, I'm going to call it MP actually. So let's say that my mass of my pulley is 3 kilograms, and the radius of my pulley is 0.5 meter. This block is hanging by a string that's wrapped around the edge, and it's enough string that it can fall, and it's going to fall 2 meters, okay? So this thing's gonna fall 2 meters down. And what we need to know is if the mass of the block is 10 kilograms. We need to know first, what is the acceleration? And then from that, we need to figure out what is the velocity when it hits the 2-meter mark. So how we do these problems is we go back to our free body diagram. That mass M has a tension up right here and a weight M, let's call this M1 just so we don't get confused, M1G, and we know it's going to drop, so we're going to have acceleration down. The pulley, and here's the new stuff. So the pulley has, at a distance r from its axis of rotation, it's going to rotate this way, right? And that's a negative. Remember, right-hand rule, that's rotating negatively. So this is negative alpha or negative omega, is how this pulley is going to rotate. At a distance r, we have a tension T. And if we put those two torques tail to tail, we see that when we turn r to T, the angle between them is -90, which means this is a negative torque. Also, alpha is negative. So what I want you to do is when you do a torque diagram, I want you to write the r vector, the force, in this case is a T, which way the whole thing's rotating, because we could have like another mass over here, so we could have another r and another T if we needed them, but which way it's rotating and whether or not the torque is negative or positive. The reason why we write free body diagrams is the same reason why we write torque diagrams. Here we can simply write M1A is, since it's down, M1G minus T. The torque diagram, we write I negative alpha. If it was positive, if it was rotating the other way, this would be positive. And then we just write the torque. Remember RF sine theta, but theta is -90. So this is negative RT. Notice the negative signs. So this becomes I alpha RT. Solve this for T, and we get I alpha over R. But alpha, remember, R alpha, whoops, come on. R alpha is A. Now why? Because at the edge, A at the edge here, the tangential acceleration of this pulley at the edge is equal to R alpha. So this alpha is equal to A over R, and I get I A over R squared. That's where I put it in. Because these are stretchless, massless, frictionless ropes, I know that this A and this A have to be the same wherever this point is. If this goes down with an acceleration, this point at this edge of this pulley rotates with that acceleration. So I get M1A is equal to M1G minus I over R squared A. I can move that and solve it for A, and what I get is M1G over M1 plus I over R squared. This acceleration is positive, but it's down. I chose it to be down, which is why I got a positive. Your book might give you this as a negative. You know it's negative from the drawing. I don't do that. Your book does. I don't know why. I for the pulley, remember, is mr squared because over 2, because it's rotating through its body, right? So this M1G is 10, and if we use 10 for G, we can do that here. 10 plus, this is 3 times a half squared, which is 4. This is 3/8 kilogram meter squared. So plus 3/8, right? So this is 83/8. So 100 divided by, this would be 80 over 80 plus 30 over 80. Sorry, yeah. So this would be 110 over 80. Or I would get 8,000 over 110, which is did I do something weird? I think I did. 80 over 80, 30, no. That seems off to me, but perhaps I'm right. I'm just being weird. my I is 3 times a half, which is a fourth, times another half, which is an eighth, so 3/8. And 10 plus 3/8, and then 100 divided, oh, yeah, I did my math, stupid. This is wrong somehow. What did I do wrong here? I don't know. Somehow I got my math messed up. 10 plus 3/8, if I did, oh, I know what I did wrong. If I wanted this to be, I would get 80/8. This would be 83/8. I'm just stupid. Sorry, guys. Can't do math. Because I want this in eighths. So this would be 800/83, which is 9.64 meters per second squared. Okay, that's how fast this thing's gonna fall. Then if I wanted to, there's always that last analysis step. Since I know A is 9.64 meters per second squared, and I know that Y initial and Y final, I said it dropped from Y initial would be 0, Y final would be 2 meters with a negative sign because it dropped, right? My acceleration is actually in the negative direction if that's true, that I'm defining Y to be down or positive up. Or what I could do is not call it negative. So let's not do that. And we would say this is 0 and this is 2. So this block drops from 0 to 2 meters with an acceleration of 9.64. Then they're both positive. Using the constant acceleration equations, I know that v final squared minus v initial squared is 2 a times y final minus y initial. Starting from rest, I get that v final is square root of 2a y final, which is 2 times 9.64 times 2. That would be square root of 4 times 9.64 is 6.2 meters per second. Okay, all well and good. We found the acceleration by using a torque diagram and a free body diagram. We set the accelerations equal, the angular acceleration and A equal, and we also had to use this to turn alpha into A, right? That way we had, because we can't solve, if this was still an alpha, we don't have enough equations to solve for our unknowns. We would need 2 equations and we only have 1. So once we've done that and we've found our A for the system, we can then ask, well, if the mass falls 2 meters, what is the velocity of the mass? This is exactly what we do for energy, although now you're going to have to, I'm sorry, not for energy. This is exactly what we do for the free body problems that you did way back in 5 and 6, although now you're going to have to include the torques, and you're going to have to relate the torques to the tensions basically, and then the tensions go into, you know, something like, imagine here you have something ugly like this, right, where you have a block over some pulley and then another block here. You would have to relate these tensions to the torques acting on the pulley somehow, right? So this would be T1 and this would be T2, and then figure out everything. But the only major change is that now the pulley has some additional mass or moment of inertia. And what your equations used to look like, remember they look like M1 plus M2 times A is equal to M1 G sine theta minus maybe M1, M2G for this, if there was no friction and this thing was sliding that way. If the pulley didn't exist, that's what this would look like. If the pulley does exist, what you'll end up with is I of the pulley divided by R of the pulley squared times A is still M1G sine theta minus M2G. The reason why I know that is I know that. If you do it the way I showed you, and we'll do these tomorrow in the lecture tomorrow, you'll get this. And basically what it's saying is now if the pulley can rotate, then it also has some mass. And remember that I is mr squared, so if we divide by r squared, essentially this is just the mass of the pulley. So the total mass times the net acceleration of the system gives you the sum of those forces. The total torque, or the sum of all the torques, gives you I alpha net for each object. So all the torques on each object you have to figure out, and that gives you I alpha. However, there's another way to do this same thing, and this becomes really nice. M, mass of the pulley, we can do this with energy. So energy initial, energy final. At energy initial, we're going to say y is 0. At energy final, we're going to say y is minus 2 meters. We have to go down because we have to use gravity. And if we use energy the way we formulated it, gravity has to go down and y has to go up, opposite of gravity. So what we write down for energy initial, and we're going to start from rest. So V initial is 0 and omega initial is 0. The initial energy, we would write M1 V1 squared over 2 plus M pulley V pulley squared over 2 plus I omega pulley squared over 2. There's MGH1. So the pulley can't move. It's not going to change its height, so we don't have to include heights. We actually don't have to include this term either because the pulley can't move. It can't translate, right? So the only three terms we have in the system is it could have kinetic energy, the pulley can have kinetic energy of rotation, and the block can have potential energy of gravity. E final will be M1 V2 squared, or V final squared if you prefer, I omega final squared over 2 of the pulley. So this is initial, so we pulley final, plus M1GH final, or H2. I guess I'm flipping I want to use finals. Whatever your indexes are though, between 1 or initial. I'm not being consistent, I'm sorry. So setting those two energies equal and just adding the energy of rotation gives you that equation. And then I'm going to write it nicely right here. E initial, E final. And then I'm going to write E initial is equal to E final by conservation of energy. So this was M1 V1 squared over 2. Nope. I omega initial squared over 2 plus M1 GH naught. And M1 V final squared over 2 plus I omega final squared over 2 plus M1 GH final. And now I note that if I start from rest, V initial is equal to 0. Omega initial is equal to 0. And I can say that H initial or Y initial was equal to 0. So H initial is 0. H final is negative 2 meters. And then I know that V is equal to R omega. So I can turn this omega into V. So what I get is all these terms are 0. 0 is equal to M1 V final squared over 2 plus I omega is V divided by R squared over 2 plus M1GH final, which is minus 2. And what I see here is that if I combine all these like terms, right, what I get is I get M1G times 2 is equal to M1 over 2 plus I over 2R squared, all times V final squared. Now I can solve this for V final as the square root of M1 times G times 2 over m1 to the half plus I over 2r squared. If I look back on what my actual numbers were, 3 and 10, so m1 was 10, mp was 3, g I said was 10, and I, we got 3/8. Yeah, I was 3/8. So plugging those things in here, and R was a half meter. Plugging these numbers in, 10 times 10 times 2 is 200, divided by, 10 divided by 2 is 5, plus 3/8 times 3/8 times 1/2 times 1 over 1/2 squared, which is a fourth. So this becomes 3/4, assuming my math checks. And the square root of this answer is 5.89. I don't know if my math checked. Nope. Let me double check my math and do it actually in a little bit better way. So this is B1, oh, I'm sorry, B final, is equal to M1 times G times 2 over M1 to the half plus I over 2R squared. This would be 10 divided by 2 plus 3/8 times 1/2 over 1 divided by 1/2 squared. So that's a fourth. That's 6/8. That's where I made my mistake. Over 10 times 10 times 2. Yeah. So 10 halves plus 6/8, 5.75. So B final is square root of 200 over 5.75, which is square root of 200 divided by 5.75 is 5.89. Is that what I got before? I feel like I've got something wrong here. Because my B final here was 6.2. Let me see what alpha should be. And alpha was I, sorry, torque over. I've got some mistake in here that I'm not going to try and find right now. Oh, I really should try and find it. Let me go through this one more time. So if I have this, my energy initial is M1GH1 plus M1V1 squared over 2 plus I omega 1 squared over 2, and these are all 0. E final is M1GH final plus M1V final squared over 2 plus I omega squared over 2, I omega final squared over 2. This tells me that if this is all 0 and H final is -2, that I get M1G times 2 is equal to M1 to the half plus I over 2R squared times V final squared. This is 10 divided by 2, which is 5. This is MR squared of the pulley, which was 3. Where did I put those stupid masses? 3 and R was a half, so that's true. So this is 3 halves times 1/2 squared, which is 3/8 kilogram meters squared. if I divide that by 2 times 1/2 is a half, right? So this is 3/8 divided by 1/2, which is 6/8. And so 5 plus 6/8 is 5.75. 75. This is 10 times 10, which is 100, so 200. So V final is square root of 200 divided by 5.75. Now, did I mess up my other thing? Because that gives me 5.89-ish. So I might have messed up here something. Let me double check my A here. And what I got was T is there, which is correct. This is I alpha is equal to RT, or T is I alpha over R, which is IA over R squared. So M1 plus I over R squared. A is 100 divided by 10 plus 3/8 divided by 4, so 12/8. That's 8.69. That's where I messed up. So where I messed up was this is actually wrong. This shouldn't have been 3/8. I forgot to put the 1/2 squared in the bottom here, which would have given me 12/8. So this becomes that's 12/8. So 80 over 8 plus 12/8, which is 92/8, and 92 divided by 8 is 11.5. So this is 100 divided by 11.5, which is 8.69 meters per second squared. And when I come to here, if I plug in 8.69, come on, stupid thing, 8.69, square root of 4 times 8.69 is 5.89, which is exactly what I found before. Sorry for messing that up, you guys. As you can see, though, this answer is exactly the same as the answer I got doing the energy. So you have two choices. Let's put this all together. You have two choices. You can do these torque problems with a free body diagram and a torque diagram, and then you'll need to write the Newton's equations, which means MA is equal to sum of forces and I alpha is sum of torques. Somehow get A to alpha or alpha to A using A is equal to R alpha, either way, and then use constant Excel to get V final, let's say. Or you could use energy and just write down the energy at A and the energy at B and C and blah, 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 and solve for V, but remembering that V and R, V and omega are related by V is R omega. It's really your choice, and you may have that choice on exam 2, or you may not. I may ask you to either solve it using free body diagrams and torque diagrams, or solve it using energy, one or the other. But really, you do have a choice. You can do it either way. The nice thing about energy is you don't need to know anything other than to include if it can rotate I omega. The one thing I should say is, imagine there were 2 pulleys here. We're going to do that problem. And in that problem, the I of the 2 pulleys gets added together and you find the torques. We'll talk about that tomorrow on some problems. I really don't want to talk about that today. But anyway, it's a lot to learn. But it's, when you're using it, it's actually not that much new from what we've done before. You just need to know how to write a torque diagram, or you need to add I omega squared over 2 for anything rotating. So are there any questions on this stuff? I'm sure there's a million that you haven't asked yet, but what I want you to do is, like I said, I put a quick homework. It's meant to be quick, online today for us. It's not due till next week, I think, but do it today, and just try and knock it out when you're doing, if you don't read the chapter today, read it tomorrow, or watch the lecture today or tomorrow. Try and do it as you study, and see if it helps you understand the concepts that you're reading about. You may need to go back and look at uniform circular motion. I think that was chapter 5. It might have been chapter 6 or chapter 4. It might actually be in both of those places. So make sure, if you need it, go back to uniform circular motion. Tomorrow, our quiz will be basically like, there's a problem in that little quick homework that shows something weird like this, but it gives you some R and some force and some other R and some other force. So this would be force 1 and force 2. And you have to compare them. So just be able to figure out, if you have R and you have force at some angle, be able to figure out what the torque is and turn that into energy. Otherwise, that's all I got for you today. You just need to read chapter 10 and make sure you understand the variables that we're talking about, and you know how to find a torque from a cross product without doing really the math, by looking and going, okay, this is R times Fy, because it has to be the perpendicular part of F, which is Fy. So this is RF sine theta. And if I put R here and I put F here, I'm turning counterclockwise, which is positive. So this torque is RF is positive I alpha. And other than that, you're good to go for tomorrow when we talk about questions in depth. Okay?
When are you going to post this recording, Professor?
Right away. As soon as I'm done, I'm going to post it in the video lectures. I'll call it chapter 10 class lecture or something, I guess.
Okay.
All right. It might take a few minutes to download and compress. The other thing, you guys, before you leave, I'm going to try to grade your free fall labs today. I meant to do that. You probably saw that I graded all your quizzes on Friday. I meant to do it Friday, but then I had the faculty meeting, and then I got caught up in a bunch of garbage this weekend. So as soon as we're done this afternoon at some point, probably not as soon as we're done, later this afternoon, I'm going to grade your free falls, and I might grade some of your vector stuff, just if you're worried about that. Other than that, tomorrow I'll post solutions to homework 4 and 5 from last week, and I'll post some practice exams for you. Okay. Other than that, I'm good. I'll talk to you all later.
Yes. And also, you said that we are able to make up points for the exam. Is it so?
Yeah, I'll put that announcement on as soon as we're done. I'll go in. There'll be a place where you can submit it. All I want you guys to do is submit handwritten solutions to the things you got marked off for. So if you look at that grade thing, it'll tell you where you missed points. And if you don't know why you missed points, on the thing, if you think that when you look at my solution and your answer that they're correct, let me know and I'll double check it and I'll give you the full points if I messed up. I messed up on somebody's test and I took some points off that I don't know why. I know why, I think, but they actually had written what I wanted. I just didn't see it. So if you think that I've graded something wrong, put it in there too, and I'll take a look at it. But what I want is just essentially, if you really wanted to, you could just copy my solution. That way I know for sure that you understand how the problem was done. Um,
Okay.
and you'll have till exam 2 to turn them in. So you'll have a week from tomorrow to turn them in. And you'll get half the points back. So if you miss 10 points on the exam, you do the corrections to the 2 things you missed, let's say 5 points on, you'll get a total of 5 points back. All right.
Okay. Yeah. Thank you so much, Professor.
You're welcome. Stay safe, everybody.
Bye. See you tomorrow.
Okay.